The final set of formulas that we cover in this chapter are the half angle formulas. And these are simply formulas that allow us to express trigonometric functions of some angle that we see could be half of some larger angle. And we're just writing it in terms of that larger angle itself. And so this is often helpful when we are dealing with angles that perhaps we can't evaluate using the unit circle, or when we are needing to make some type of trigonometric substitution. Now, I've written out the half angle formulas for you here, so you can pause the video and jot these down if you'd like. I'm not going to derive all of them, but just wanted to do a really quick and easy proof of one of them. So if I wanted to just do the proof of, for example, let's say the cosine one. Let's just do the cosine one real quick. So I'll do one of these and hopefully you can kind of get the sense of how you do the rest. But we would actually prove this using the double angle formula. So I'm going to actually start with saying cosine of 2 theta. And we know that the cosine of 2 theta can be equal to a couple of different things, but I'm going to actually rewrite it in terms of 2 cosine squared theta minus 1. Now, I'm going to actually also define and temporarily just redefine 2 theta as being some other variable, which we'll call x. So let's say x is equal to 2 theta, which then means we can then say the following. That means theta is equal to x over 2. You can probably see where this is going now. Well, if I replace 2 theta with x, I can say cosine of 2 theta is equivalent to cosine of x. And over here on this right side, I want to make another substitution. I'm going to say 2 cosine squared, and instead of theta, I'm going to write that as x over 2 minus 1. And at this point, it's just a matter of doing some inverse operations. We're going to write this as cosine of x plus 1 is equal to 2 cosine squared x over 2. Then we're going to go ahead and divide everything by 2. So let me actually just do that in the same step. And since I notice that this is 2 cosine squared x over 2, I'm going to actually take the square root of both sides. So that all means that the cosine, and I'll just clean this right side up here, that the cosine of x over 2, or in this case, the cosine of half of some angle x, is equal to this. And you notice, hopefully you're noticing that I'm missing something. Anytime we extract roots or take the square root of both sides, I have a plus or minus there. So we see now that the cosine of half of some larger angle x is equivalent to plus or minus, meaning the positive or the negative square root of cosine of that angle x plus 1 over 2. And again, this on an algebraic level may not make a ton of sense just yet, but hopefully when we actually start seeing it with specific values, this will make a little bit more sense. So let's try an example now. So let's find the exact value of cosine of 105 degrees. So you'll notice that 105 degrees is not an angle that we're accustomed to working with on our unit circle. So we have a couple of options. We could use sum and difference formulas. We could rewrite cosine of 105 degrees as the cosine of 60 degrees plus the cosine, or plus 45 degrees. And we covered that in a previous video. So go back and look at my video on sum and difference formulas if you need help on that. But alternatively, we could also say that, all right, well, 105 degrees, let's treat 105 degrees as if it is half of some larger angle, if you will. That is to say, 105 degrees, this is going to be our u over 2. And so 105 degrees is half of what angle? We would say u is equal to 210 degrees. It's double whatever 105 was. So writing the cosine of 105 degrees, if I use my cosine formula, which again, cosine is plus or minus the square root of 1 plus the cosine of whatever your angle u is. And we just said angle u will be twice as much as 105. Okay. And then this is going to all be over 2. So now from here, I'm just going to evaluate. I'm going to say plus or minus 1 plus, and what is cosine of 210 degrees? Well, that would give me negative root 3 over 2. So let me just write 1 minus root 3 over 2. All of that over 2. And this is all in the square root. So let's clean this up a little bit. In our numerator, we can write this as 2 minus root 3 over 2. And we're dividing all of that by 2, which then allows us to write plus or minus 2 minus root 3 over 4, which can be cleaned up as root 2 minus root 3, all of that over 2. And now would be a good time to discuss this whole plus or minus business. What's happening with that? Well, right above, I wrote a note that the sine of cosine of u over 2 and the sine of u over 2 depends on which quadrant that u over 2 lies in. That is to say, don't lose sight of what we're originally trying to do. We are simply trying to find the cosine of 105 degrees. That is our original problem. That is to say, what quadrant is 105 degrees in? Well, 105 degrees here is in quadrant 2. It's this angle here. This is 105 degrees, roughly. We're in quadrant 2, and in quadrant 2, cosine must be negative. Therefore, we would say that our final answer is negative here. Now, had u over 2 or our half angle been in quadrant 1 or in quadrant 4, then we would have then kept that as positive. So this is the case for both sine and cosine, where you should look at what the cosine or sine of u over 2 is to help us evaluate there. Okay, so that's our final answer. All right, let's try one more example of this, something kind of similar here. We notice that we're told in this next problem that sine of u is 5 over 13, and angle u is in quadrant 2 because it's between pi over 2 and pi. Well, we don't know exactly what u is. We'd have to use inverse trig functions to figure that out, but what we do know based on our information is that angle u is in quadrant 2. Let me just draw a right triangle to represent angle u. Angle u is in quadrant 2, and we also know that the sine of angle u is 5 over 13. Well, if we look at these side lengths, we notice, or hopefully notice, that these are the side lengths of a Pythagorean triple. And if you didn't know that, you could always just do the Pythagorean theorem, but you should arrive at our adjacent side being negative 12. Well, based on that, let's find the sine of u over 2. Okay, so that's our first one, sine of u over 2. Well, the formula for sine of u over 2 is pretty similar to the formula for cosine, where it's 1 minus this time, 1 minus cosine of u, all of that over 2. Now, I previously discussed the plus or minus, so let's actually just take care of that now. Some students like to take care of that at the very beginning. Otherwise, quite honestly, they just forget to do that, and they leave their answer in plus or minus form. So let's figure out if it's a positive or negative value. Well, if angle u is in quadrant 2, where does half of angle u have to be? Well, angle u over 2 would have to be somewhere here in quadrant 1. It's got to be somewhere here in quadrant 1. U over 2 would have to be here. Just think about it this way. There's no way that u over 2, or half of u, could be in quadrant 2 so that when you double it, you're still in quadrant 2. That just wouldn't make any sense. We would have to be in quadrant 1, right? So in quadrant 1, we know that sine is positive. Therefore, we're going to keep our answer as positive. Okay? All right. So now let's finish evaluating. So we got the positive, 1 minus, well, what is the cosine of u? Again, I don't know what u is, but I do know that the cosine of u is negative 12 over 13, and all of this divided by 2. And so from here, it's just cleaning up. We can rewrite 1 as having been 13 over 13. So then this would be 25 over 13, all of this divided by 2. And so this is root 25 over 26. And this would be just 5 root 26 over 26. Okay? All right. Go ahead and try to do the rest of these for cosine of u over 2 and tangent of u over 2. Okay? All right. I wanted to do one solving problem and one verifying problem, so let's run through a few of these. Let's solve using the half angle formula. So this is another example of when we would want to use the half angle formula, because we're looking at this equation right now, and without the half angle formula, there's really nothing else that we can do. So I'm going to actually rewrite the sine of x over 2, rewrite all of this as plus or minus 1 minus cosine of x, all of that over 2. And I'm going to write that as plus or minus because I don't really know what x is or where x over 2 is. So I can't establish whether or not it's positive or negative. But I can make that substitution so far. Now, I notice that this is all in terms of cosine, so I can go ahead and write, I can write plus cosine x minus 1 is equal to 0. Okay. So in my next step, I'm actually going to move all of this over to one side. So I'm going to write 1 minus cosine x to, that is to say, I'm going to want to move these terms over to the other side. So I'm going to write this as 1 minus cosine of x. And the reason I'm doing that is so that I can go ahead and square both sides. You remember, if we have a radical, oftentimes we want to move the other terms to the other side so that we can negate that radical. Squaring a positive or negative is always going to result in a positive, so I don't have to worry about that plus or minus anymore. If I expand this right side, this is 1 minus 2 cosine x plus cosine squared x. And then from here, we can start combining like terms. Multiply both sides by 2, and then, so we can write 1 minus cosine x is equal to 2 minus 4 cosine x plus 2 cosine squared x. And then if I move all my terms to one side, we can get the following. 2 cosine squared x minus 3 cosine x plus 1 is equal to 0. And I believe this is factorable. Let's see. This is 1 and this is 1, and these are both negative. Yep, I think that works out. So I can then say from here, let's go ahead and write cosine x is equal to positive 1/2. Cosine x is equal to 1. X is then equal to both pi over 3, 5 pi over 3, and 0. Now I should note here that I am boxing my answer, but we should be checking for extraneous solutions because we went ahead and we squared both sides. So there is a possibility that we created more solutions than there were, but here in general, we would hopefully see that all of these do work out. So I'm not going to show the check, but you can try it yourself and hopefully you'll find that they all do work out. Okay. All right. Let's go ahead and try this verifying one now. So you can try to pause the video and work through it on your own. And you'll hopefully find that there was a couple of ways to do this, but what I did is I actually went ahead and rewrote this left side as 1 over cosine of u over 2 to start. And the right side is quite a bit to write, so I'm not going to keep writing it, but I'll draw my arrow in just a moment, which then allows me to rewrite this as pretty much the reciprocal of the half angle. This is just another way of saying the reciprocal of the half angle. So the reciprocal of the half angle formula for cosine is the following. That's the reciprocal, right? So from here, I can then write this as 2 over 1 plus cosine of u. And I do know that I want to end up with tangent in my numerator here. So what I'm actually going to do is I'm going to multiply both the top and bottom by the tangent of u. Extend that out. And so this allows me to then write the following. Plus or minus 2 tangent of u. And if I distribute that tangent of u in the denominator, I got tangent of u plus cosine of u times tangent of u. And then from here, 2 tangent of u plus cosine of u. I make a simplification here, sine u over cosine u. And we're pretty close from here. At that point, these cosine u's would divide out. So we have 2 tangent of u all over tangent of u plus sine u. And that is exactly what we were looking for in the original problem. So I'm going to draw my arrow, extend that all the way down, and write that plus or minus, and just write it again. Just to establish that, yeah, we did indeed rewrite one side so that is exactly equal to the right side, therefore proving that the first statement is indeed logically true. All right, so those are some practice problems working with the half angle formulas, and hopefully you can see some uses for it now when it comes to solving, verifying, and evaluating.